Alright, y'all, welcome back to Bon Science. Today we are going over Unit 1, Topic 6 in AP Chemistry, which is the photoelectron spectroscopy of elements. So let's just get straight into it. Okay, so what is photoelectron spectroscopy? So photoelectron spectroscopy is a technique that scientists use to determine the atomic structure, so to figure out the structure of an atom that they're studying, and specifically it's how they figure out the electron configurations and the way the electrons are arranged in the atom. So you don't really need to know what's going on in photoelectron spectroscopy. You can look it up if you want. It's some like really cool physicsy stuff. But what you do need to know is you need to know how to read a photoelectron spectrum. Photoelectron spectrum. And if you're wondering what that is, it's the graph that's right in front of you. The one with binding energy and relative number of electrons. Because when scientists do photoelectron spectroscopy, this is what they get. They get these graphs, which are called photoelectron spectra, or photoelectron spectrum. And so specifically, this one is of silicon. I pulled this from an APFRQ. So that's that. They'll usually tell you what atom it is, but what you need to be able to do is figure out the electron configuration when you're looking at one of these. So if you're going to do that, you need to understand what's going on in this graph. So let's cover what's going on. So first, you can see on our x-axis we have binding energy. You can think of this as the energy it would take to remove the electron from the atom. So how much energy would you have to put in to remove the electron? Because the electrons, they're attracted to the protons, right? So they want to stay where they are because they're being pulled by the protons. But if you wanted to remove that electron, you'd obviously have to put force in, right? It's like when you're lifting someone up from Earth, gravity is trying to keep them down. So you have to put in some force and put in some energy to lift them up and move them. Same thing with an electron. And one thing you might have noticed is that the bigger number is on the left and the smaller numbers on the right, which is like the opposite of a normal graph, right? Usually you start with the smaller numbers and you go up to the bigger numbers. It's like the opposite here. The reason it's like this is because binding energy is technically negative, just because electrons are negative in charge. So when you do the math, you get a negative sign. But in nature, signs don't really matter. What matters is magnitude. So like technically this number is negative 1,000 and technically this number is negative 0.1. So negative 0.1 is bigger mathematically than negative 1,000. So we put negative 1,000 on the left. But in terms of magnitude, negative 1,000 is bigger, right? Oh, sorry, notification. But technically negative 1,000 is bigger. So, it's a little confusing, but just basically the bigger numbers are on the left, but they're still bigger. They still represent more energy. Then on the y-axis, you can see we have relative number of electrons. So basically, that just means that the height of the peaks just represents the amount of electrons, right? So like this one has 2 electrons, this one has 6, this one also has 2, right? And this one has 2 as well. Easy stuff. One other thing you should know, each peak represents a different subshell. So that's from the last episode of electron configuration, right? So like S subshell, P subshell. For the AP, you'll only ever see spectrums with the S and P subshell, so don't worry about D or F. And then each group of peaks represents an energy level. So this peak that's all alone here, that's one energy level. These two that are clumped up, that's another energy level. And then this one that's alone is another energy level. So that's like the basics. So then how do you figure out the electron configuration from this? Well, the first energy level is closest to the nucleus. You should just know that. It's the closest to the nucleus. Electrons on the first energy are closest to the nucleus. So if you remember from the last episode, we have Coulomb's law, which says that force and distance are inversely proportional. So if you have less distance between two charged particles, they experience a larger force, which means that they have more energy. So the electrons that are closest to the nucleus, the ones on the first energy level, are going to experience the largest force, which means they're going to have the biggest energy. So that means that this is our first energy level. Alright, and then the only subshell on the first energy level is the S subshell, and there's 2 electrons. So that's actually 1s2 right there. And that's how it is for every single spectrum. The first peak is the 1s. And then it might be 1s2, it might be 1s1, it depends. So then we jump over. The second energy level is a little farther, so it experiences a little less energy, right? The first peak is the 2s subshell at S2. Second peak is 2p. So S comes before P, always. So that would be 2s2, 2p6, and then we jump again, and that's 3s2, because it's too tall. So that's our electron configuration. That's how you figure it out. Pretty easy. You always start with 1s2, and then S comes before P. It also makes sense because P is taller, so like S can't hold 6 electrons, so there's no way this second one over here could be S. Doesn't make sense, so it has to be P, right? And this is how we actually know that there's different subshells, because they show up as different peaks. So we know that like the P subshell is like a little farther away, but like it's still on the same energy level because it's so close to the 2s subshell. And that's really all you need to know. You need to understand why the peaks are at different points, and that's just Coulomb's law, right? So if it ever asks you a question about why the peaks are different, like energies, it's because of Coulomb's law. The ones at the smaller energies are just representing electrons that are farther away, so they experience less Coulombic attraction. And the ones that are closer to the nucleus, so they experience more Coulombic attraction, stronger force, and so they have a higher binding energy. But that's really all you need to know about this lesson. So I hope you found that helpful. Make sure to like and subscribe, and I'll see you for the next one.